Okay, so today I will show you our recent result about molecule pairs, organic pairs. So maybe you are not that familiar with single molecules, so I just make a short summary of what they are. So basically, they are fluorescent organic molecules, which an electron, a pi electron, which is delocalized over the structure, and these molecules are embedded in a matrix in a crystal, and they are placed inside a chrosat at 2 Kelvin. So the pi electron is localized over the structure, which gives rise to energy level, S0, S1, and so on. And then on top of them, we have some vibrational levels. So usually we use a laser that excites the molecule from the ground state S0 to S1, and then the molecule can either radiate photons through the zero phonon line, so an emission of photons without any phonons, or redshifted photons, where the molecule will give rise to the emission of the photons and then the emission of the phonons. So the typical lifetime of the S1 state is 10 nanoseconds. So due to the spin-orbit coupling, we can transfer the molecule into a triplet state, but this intercrossing system in our case is extremely small, of the order of 10 to minus 8, which means that we can neglect this part of the diagram, and our system behaves like a two-level molecule. So why molecules are that interesting? So if you would like to compare to other systems in solid physics, so we can compare to quantum dots or NV center. So molecules are extremely photostable. You can excite them for seconds, hours, days, or even months without any photobleaching. So they behave like a two-level system. There is no dephasing. And if you look to the photons which are emitted on the zero phonon line, what is interesting is that they are fully indistinguishable. And if you would like to compare to atoms or ions, so molecules are trapped inside the matrix, so we do not need to cool them with laser procedure, and we can use microscope objective with very high collection efficiency to detect all of the photons from the molecule. And what is interesting also is that the optical cross-section is the same as the one for an atom, which is 6 to 10 minus 10 centimeters square. So in the talk here, I will show you what we have done with DB-ATT molecule, our fluorescence molecules, which are embedded in the naphthalene. So how do we observe this kind of molecule? So the first observation has been done in 1990 in Bordeaux. So where they use a laser, and then they shine the laser onto the sample, and then they scan the laser on the zero phonon line, and by scanning this, we can collect the photons which are redshifted, and we can observe very sharp and intense peak, which each of these peaks corresponds to one single emitter. The frequency of these emitters is distributed over the inhomogeneous line width, which is typically ranges from tens of gigahertz to nanometers, depending on the sample that we use. And if we zoom on one, what we will see is that we will have a very sharp and narrow Lorentzian line, which is 20 megahertz, which exactly corresponds to the lifetime of the excited state, which is 7.4 nanoseconds. Okay, so what can we do is that first we can try to use this molecule as a qubits. So the first thing is that we would like to induce a Rabi flopping from the ground state to the excited state. And the best way to do that is that we just shine a light on this system. And because the molecule is trapped inside the matrix, they do not suffer to any heating due to the laser field. And in this configuration, we can send a light which is 6,000 times larger than the saturation intensity. And in this condition, we can induce Rabi oscillation at a gigahertz frequency. So here we observe more than 16 Rabi flopping. And the decay of this curve is, again, given by the lifetime of the excited state. So there is no dephasing. So to have a proof of that, what we have done is that we have performed a Ramsey spectroscopy, which consists of sending 2 pi/2 pulse on the molecule. So the first pi/2 pulse will bring the molecule from the ground state to a coherent superposition between the ground state and the excited state. And then we wait for a certain amount of time, and then we apply a second pi/2 pulse to bring the molecule from the EG to the G state. And then we look at the population as a function of this delay time. And what we see here is that we have a decay, an exponential decay, which corresponds to 14 nanoseconds, which is twice larger than the lifetime of the excited state. We also increase the temperature of the, so this has been done at 2 Kelvin, so without any dephasing. And what is interesting is our cryostat is that we have a knob, which is the temperature, and then we can increase the numbers of phonons inside the matrix. So we repeated the same curve at a temperature of 9K, and what you see here is that you have a strong decay of the population as a function of the time tau, which is just the observation of the dephasing due to the phonons. So now the question is, I hope that I convince you that the molecule is a good quantum qubit. Now, how can we scale up the system? How can we find many molecules nearby? Actually, the solution is not that easy. I will not enter into too much detail how we can find 2 molecules nearby, but we can do this, as I will show you. And then we would like to make them really close, to make them interact through the dipole-dipole interaction. So if I look to the Hamiltonian, so you will have the Hamiltonian part corresponding to the 2 independent emitters, and the dipole-dipole interaction, which couples the two. If we are in the resonant case and for a distance between the 2 emitters which is much smaller than lambda, then the expression scales like this. So the first thing is that, as you see, V is scaled as 1 over d cubed, which means that you need to have the 2 emitters really close to have a V which is larger than the lifetime of the excited state. So typically D should be of the order of 10 nanometers. So this is the first thing. And the second thing, what is interesting also is that depending on the orientation of the 2 dipoles, whether it's like this or like this, the coupling constant can be either positive or negative. So if we look to the diagram, what is interesting here, that you have 2 intermediate states which are entangled, S and A, which are a current superposition of having the first molecule in the excited state, the second one in the ground state, plus the first one in the ground state and the second one in the excited state. So this is the symmetric one, and you have the antisymmetric one, which is exactly the same with a minus. So classically, the picture of these 2 states correspond of having 2 dipole oscillating in phase, or 2 dipole oscillating with a pi phase shift in between. So the S state and the A state are either in this configuration or inverted, depending on the sign of V. And to see this is what we have done here. So we scan the laser through this 3 transition, and we record, as before, the numbers of counts that we get for each of the frequency. So what we see here, we see 3 peaks. So we have one sharp here and less intense, which corresponds to the antisymmetric state here. This one corresponds to the superradiant one. So we are in the G configuration. The antisymmetric state is above S, which means that V is negative. And what is interesting also is that at the center of this spectrum, you see a 2-photon transition, which means that you can directly excite the system from the ground state to the doubly excited state E. And this, the amplitude of this signal scale as the square of the laser intensity as predicted. So we found many pairs. So these are 4 examples of pairs that we have been able to find. Actually, molecules are trapped inside the matrix, which means that you could not control V. D is fixed, mu1 and mu2 are fixed. So now the question is, from one of these pairs, how can I play with the degrees of entanglement, which means how can I decouple, go from pure Bell state, EG plus GE, to a separable state, which is like EG or GE. So what we have done here is that we have changed the frequency of the two emitters, omega 1 and omega 2, by using some electrodes which are placed under the sample, and then we are recorded this same excitation spectra for different applied voltage. So at very negative voltage here, what we see is that the two peaks are well separated, which means that the frequency of the two emitters are really different, which means that, and this is what we can observe here is that the width of this peak and these peaks are similar with typically the same amplitude. And as soon as we increase the voltage, what we see is that the two peaks are getting closer and closer up to the resonance, which is here. So the distance here in frequency gives you the value of the coupling constant. You see that the two photon transition increases, and more importantly, what you see is that you have a broadening of the superradiant transition and a sharpening of the subradiant transition, which is the fact that first these two lines are superradiant and subradiant, and the fact of optical selection rules. So we use the master equation to model our system, and we found a very good agreement between our experimental data and the model. And in this case, we were able to go from a quasi-separable state to a quasi-Bell state here. So the parameters of the pair is that V is equal to 10 gamma 0, so we're in the strong coupling regime, and the estimated distance between the two emitters is typically 25 nanometers. So I told you that here we have some superradiance behavior, and here we have some subradiance behavior, but for the moment you have to believe me that we can have this information from this spectra. If we would like to do the direct observation of this effect, what we have done is that we have sent a pulse at resonance either with the superradiant state, the blue one, or the subradiant state, the red one, and we have recorded the time evolution of the fluorescence at the end of the pulse. And the decay of this pulse, of this fluorescence, will give you the lifetime of the excited state. So here we compare these two measurements with 35 other independent molecules, and which the average are around 7.8 nanometers. And as you see, the two points are clearly outside of the distribution. So one will ask me why your subradiant state is not completely dark. Actually, our system is not it's not two level systems. We have these vibrational states, and these vibrational states are not currently coupled from one molecule to the other one. And then we have to modify the two lifetimes, so the superradiant and subradiant, taking into account what we call the Debye-Waller factor, which is the ratio between the intensity of the zero phonon line, which is here, compared to all of the vibrational lines. And in this case, we can find a very good agreement with our measurements. And what we have done here is that we modified the molecular detuning between the two, and we find that we can modify the superradiance and subradiance behavior of the pair, and we found a very good agreement between the calculation and this Debye-Waller of 0.3. So yes. So do we have other information that we can get from the system? The answer is yes. So we would like to do the second order correlation measurement. So we shine the laser, and then we put a we go in the start unvariable and twist configuration with a start and a stop, and then we recorded this G2 for the 3 configurations. So either the laser is at resonance with the superradiant state, subradiant state, or on the 2-photon transition. For these 2 states, what we get is that we get a strong anti-bunching. This is due to the fact that we have only 1 excitation at one time in the system. If we send the laser, if you tune the laser to the 2-photon transition, what we will see is that we will see a strong bunching, and this bunching due to the fact that we will go directly from G to E, and then we will have a radiative cascade. So after the first photon, you will have a second photon. And this is the explanation of this strong bunching. So as an experimentalist, we decided to model this system by saying that first we detect a photon start, which resets the system in one of these 4 states, and then to get the probability of having the second photons arriving in time tau, what we have to do is that we have to compute the population of the system, either starting from the superradiant state, from the ground state, or for the antisymmetric state. However, in this case, we do not have all of the information, especially we miss the optical coherences of the system. So we have a collaboration with here, with the DIPC, where we decided to compute the G2 using the second quantization of the field with the operator E- and E+. And what we would like to do is that we would like to look to the Stokes-shifted photons, which means that the field operator will be given by this operator, which goes from E to V or V to E. We use this master equation to determine the G2 function, and what we obtain is that we can divide this expression in 3 terms. So the first term, which is the green one, corresponds to our naive interpretation without any optical coherences. But on top of this, we have 2 other terms. The first one, which corresponds to the off-diagonal term of the intensity operator, which is a sharp peak at t is equal 0, which corresponds to unvariable effects of the detected photons. So these 2 paths are indistinguishable. You have to add it in. You have to add the amplitude, and this gives rise to this sharp and intense peak. With width is given by the lifetime of the vibration. And then we have the last term, which corresponds to all of the other terms and accounts for quantum coherence of the field and of the pair. So we use so we shine a laser at resonance with the 2-photon transition, and what we see is that we compare these 2 models, the green one, which is less pronounced at the center, with a peak which is shifted by pi/2 compared to the red one, and what we see here is that we have a strong disagreement between these two curves. So with the full quantum model, what is interesting is that if you remember for 2-level system, then the optical coherences started with a phase which is in advance by pi/2, and this is what we have here. So the phase started before than for the green one, and this is what, I mean, the frequency is the same, but all of the curve is shifted by pi/2. And if we compare this, so we did this in 2 configurations, so either at resonance with the 2-photon transition or slightly detuned by gamma 0, and we found a very, a better agreement with this full quantum calculation than with our naive calculation. So I think it's time for me to conclude. So I think I show you that we use ultra-stable quantum system. We can excite them for weeks. We can manipulate this qubit at the sub-nanosecond time scale. We can control the degrees of entanglement using sharp field. And we start to observe quantum currencies in this delocalized system. So the next step will be to look at how we can perform some quantum logic gates in this kind of system, like entangle and disentangle on-demand the system on a time scale given by the lifetime of the excited state. We also have another work that has been done in collaboration with the IPC, where we look to this correlation, but not on the redshifted photon, but on the zero photon line. And we would like to apply this. I mean, we would like to apply this kind of calculation to our experiment to check that this is true. So I would like to acknowledge all of the people which are involved in this project, the people from my group, and the other ones from LOMA and from the ICP. I thank you for your attention.
Thanks, Jean-Baptiste. Questions, comments?
Thanks for the talk. So I guess for the experiments you are doing, you don't want this, but if you want to go like more in the quantum information side, like more in the quantum computing side, you would eventually need to increase your decay time or your T1, no? So what could you do to change your T1, to increase your T1 in your experiment?
It's not that easy. That's the first thing. So this is the, actually we took the opposite option. Say, okay, we have the T1, we're going to do nothing with that. Could we go faster than this? And this is what I try to convince you that inducing this Trebbia oscillation at the gigahertz range is good enough to, I mean, for the moment, we are limited by technical things like the time response of the APD and stuff like that. To go, I mean, you can imagine to put molecules on a, I mean, what you would like to do is that you would like to kill all of the, I mean, killing the zero photon line and photon, it's not that, I mean, it's easy. You just have to put, I mean, easy. When I say easy, it's experimentally challenging, but you can put the molecule inside the cavity. The problem is that for the ZPL, it will be easy, but for all of the vibrations, it will be much more difficult. You can imagine to put it on 2D materials where you could not emit the photons, I mean, or kill the photons, but it's not that trivial. I would like to do the opposite. I mean, go faster and try to do.
Any other question? If not, we thanks again Jean-Baptiste, and we move to the thinking.